Okay. Hello, everyone. Thank you, Fernando, for this wonderful introduction. Well, I'm kind of excited about this lecture we're going to take today, and we're going to be taking in the following weeks about efficient heating and cooling technologies. In this first lecture, we're going to talk about the technologies themselves, and in the next lectures in the following weeks, we're going to be more focused on the energy efficiency measures in these technologies. So let's move forward. This is going to be the agenda for today. We're going to make a brief introduction to the topic. Then we're going to talk about the energy demand and the energy consumption, production systems, distribution systems, thermal systems, and ventilation systems at the end. Okay, so first of all, heating and cooling are part of something wider, which is HVAC. I believe most of you know what is HVAC, but it stands for heating, ventilating, and air conditioning. And this includes mainly three systems, which are production system, distribution, and thermal systems. Production systems involve, boilers, chillers, radiation systems, at the end, systems that produce energy, thermal energy in this case. Then we have distribution systems, which are the ones who tries to distribute all the thermal energy throughout the building. And finally, we have the thermal systems, which are, radiant floor, normal conventional radiant systems, radiator systems, fan coils, air handling units. And all of these, the HVAC, can be affected by comfort parameters such as temperature, humidity, or air quality, and also by other influential factors such as weather, size, occupancy, and isolation. Well, you might be wondering why this could happen, why the weather, for instance, or the temperature can affect in the energy efficiency ratio of, let's say, a chiller. Let's put an example here. Imagine a chiller in Cordoba, in the southern part of Spain, and imagine it also in France. Well, apart from that, the thing that in France the chiller is going to work much less hours than in Spain because of the weather and the temperature, the outside temperature, but also the energy efficiency ratio is going to be much higher in France than in Cordoba. And that is because the energy exchange, the thermal exchange in the chiller is going to happen in France at 20 to 25 degrees, and in Cordoba is going to happen at 45 degrees. And that reduces a lot the energy performance of the chiller. So it does affect these parameters to the energy efficiency of not only chillers, but every system, every producing system. Okay, so before going any further, I would like to discuss a little bit about the difference between energy demand and energy consumption, because there is a little bit of misconception in these concepts. Energy demand is the actual energy you're going to need for acclimatizing a room or a building. And the energy consumption is the current energy you're going to spend actually in acclimatizing that room. So let's say you make some calculations and it turns out that for a certain room of a building you need 100 kilowatt-hour per square meter to acclimatize, okay? Doesn't matter if it's for heating or cooling, doesn't matter. And let's say for heating. You want to heat that room with a boiler. Okay, let's say the boiler has an energy performance of 90%. So your energy demand is going to be, as I said, 100 kilowatt-hour per square meter, but your energy consumption is going to be 110. Okay, so as you can see, these are the difference. There is not the same talking about energy demand and energy consumption anymore. Okay. So as you can see in this slide here, we have a square which is like the outside part of a building. This square here, the little square in the center, would be the building, and the inside of the building is going to be the heated area, the acclimatized area. We want to acclimatize with, in this case, winter. With heating, because we are in winter. Okay, this is the case for winter. So when sizing an installation of an HVAC installation, we have to understand all the inflows, thermal inflows and thermal outflows that we have. So in this case, for winter, we're going to have these inflows, these thermal inflows, which are helping me in acclimatizing the room. These are going to be radiation, occupancy, radiation from the sun, occupancy from the people who live or work there, equipment, and lighting as well. And the outflows are going to be conduction and infiltration. These are going to be, this is regarding the envelope of the building. So as this is going to help me and this is going to hurt me, the quantity of the energy demand, the heating demand, I have to put inside the building, inside the room, is going to be the subtraction between this and this inflows and these outflows. Okay, so in the next example would be summer. Okay, so for cooling, we're going to have as well inflows and outflows. In this case, we're going to have the same inflows, but in this case, these inflows are hurting me. I don't like radiation in summer, I don't like occupancy, I don't like equipment, and I don't like lighting. Okay, because in summer, what we need to do is to take heat from the building and take it outside. Okay, so, and the other thing we have here, there are here two outflows or inflows depending on the hour of the day. At the first hours of the day, it is probable that the exterior temperature is going to be much lower than the interior temperature. So these are going to help. But at the latest hours of the day, this is going to hurt. So in this case, the quantity of heat I'm going to take out the building is going to be the sum of all these inflows. Okay, but sometimes these are going to change. This is going to the timing is going to be changed. So let's go into production systems now. So there are different ways to generate heat and cold. To generate heat, we can use boilers or electrical systems such as electrical resistance systems or heat pumps. And talking about cold, we can use heat pumps or chillers and absorption systems. Okay. So let's talk first about the heating systems. Well, I'm sure you all know what is a boiler, but let's go a little bit deeper, okay? A boiler is an enclosed vessel where a combustion takes place. And as you know, for a combustion to take place, you need air. But not any quantity of air. You need a certain amount of air, because if you have a lot of air, your fuel is not going to burn completely. And if you have little air, your fuel is not going to burn at all. So there are many parts in a boiler, but one of the main ones is the burner. The burner is here, is this gray thing here, and its aim is actually to somehow find and expel the right mixture between fuel and air. Okay, and it has to be the good mixture. It has a ratio, okay, and it mixtures and expels both things into the combustion chamber. This is one of the main things for the reduction of energy performance in a boiler. It is very important to have a correct preventive maintenance in the boiler for this to be completely adjusted. okay, this mixture. Okay, another part of the boiler is the combustion chamber, which is obviously where the combustion takes place, and is the place where the heat exchange between the chamber and the liquid, in this case water. Once the water is completely heated and warmed, this water is going to be distributed throughout all the building, throughout all the distribution systems. And finally, what we have here is the steam outlet, which is exactly where the steam goes out. The temperature of the steam is going to be very important, as we will see in the next few slides. The temperature makes a boiler to condense or not to condense. So, boilers can be classified based on different parameters: by type of combustion, by efficiency, and by fuel type. So by type of combustion, there are two types, which are atmospheric boilers, which are actually the typical old boilers you can find in lots of buildings even today. But nowadays they are in some places forbidden, so you are not likely to see them anymore around. And their characteristics is to have the combustion chamber connected to the outside air. So it is not very, very efficient, And the other type is seal boilers, which are, the usual boilers you're gonna find in every manufacturer nowadays. Also, we can classify them by efficiency. And in this type, we have conventional boilers and low-temperature boilers or condensing boilers. These two types of technologies are not exactly the same, but they work pretty similarly. Actually, nowadays, manufacturers have been discontinued the low-temperature boilers to the condensing boilers because the condensing boilers are more used, let's say. And also we have boilers by fuel type. We have boilers which can work with coal, biomass, diesel, fuel, natural gas, propane, butane, so a huge variety of fuels for every boiler and in every kind of situation. Let's do now a comparison between the different types of boilers. I've selected these two types, conventional and condensing boiler, because they are the main ones you can find. Both conventional and condensing boilers can operate at high temperatures, as you can see here, main feature. Okay, but it is true that conventional boilers are designed to work at high temperatures and are designed to work at full load. Okay, while at the same time condensing boilers are not designed to work at full load, but at a partial loads, and they are designed to work at lower temperatures, such as 40 to 55 degrees, more or less. At those temperatures, the condensing boiler can achieve this performance, 100 to 108, 105, more or less. And this is because it uses the energy provided by the water vapor, water steam in the fuel. That is why it goes above 100. So, yeah, the performance in conventional boilers, as they can condense because of as they always work at high temperatures, at maybe 80 to 90 degrees, the steam coming out of the boiler is so hot that it can condense. So conventional boilers can take advantage of the water heat, let's say. The used fuels for conventional boilers, there are a huge variety of fuels which can be used by conventional boilers. However, for condensing boilers, we could only use them with these two fuels, natural gas and gas oil. Okay, well, also, and obviously, the conventional boilers are much cheaper than condensing boiler. And well, because of this difference in performance, condensing boiler can achieve more than 25% of savings, depending on the situation. Well, this is more or less what Hagi said, but the choice of temperature depends on the boiler feed water, and this is related to the terminal elements of the heating system. So depending on your terminal units, you're likely to select one boiler or another, a conventional or a condensing boiler. If in your building you have radiation systems, conventional radiator systems, which normally works at 80 to 90 degrees, you're likely to select a conventional boiler. But if in your building there are radium floor systems or flame coil units, then you're more likely to use a condensing boiler because with this temperature, with this operating temperature, you're more likely to take advantage of the condensing feature. Then we have electrical systems, such as this little radiation system, electrical radiation system, which is based on the Joule's law, you all know. Well, the operating mode is simple. We have a flow which goes through an electrical resistance and goes out heated. This heating is achieved by using an electricity current. And the thing of this, the wonderful thing about this equipment is that they are really, really high performance. They can achieve performance of more than the 99%. They are close to the 100% of performance, which is a lot, which is very good. The thing is that they have a very poor performance of the cycle. And what does this mean? Well, it means that at the beginning, before having the electricity, we need to have fuel. And we burn these fuels into big, huge power stations in the electricity country system to make heat. And this heat is then converted into electricity and distributed through all the grid, all the country grid, with all the losses and all that stuff. And when it arrives to our houses or our offices, and we put inside this electricity of this type of system, we're going to make again heat. So we are kind of repeating things here, and we're losing energy and obviously efficiency in the process. So that's why we talk about poor performance of the cycle. And also, it is very important to understand that the electricity which this equipment needs to work is it's a lot more expensive than the equivalent in thermal energy. The electricity kilowatts, it is about 3 times the fuel kilowatt hour. So not a good thing to have in our installations. Electrical systems. We have also the heating can also be produced by heating pumps. Well, I'm not going to go very deep in the heating pumps here in the operating mode, but you all know you have the main parts of a heating pump are going to be the expansion valve, evaporator, compressor, and a condenser. The good thing of this equipment is that they have really high performance. This term is the coefficient of performance, okay? And it stands for coefficient of performance. This is a very good system because it is really high efficient. It could achieve more than 400% of efficiency. And that is why and that is because the heating pumps uses not only the electricity coming into the compressor, which the one we're feeding the compressor, but also this systems take the heat, the remaining heat from the air, and that is why most actual current regulations in some countries are taking heat pumps, not all the power generated, but a big part to be as renewable energy, because it takes the energy from the air, the remaining energy from the air. Okay, let's move on into cooling systems. As I told you before, we can generate cold with heat pumps and chillers. Okay, so now we're going to talk about chillers, which bear many similarities with the heat pumps already discussed in the previous slides. Basically, chillers are heat pumps which only generate cold. There are mainly three types of chillers, namely air-to-air, air-to-water, and water-to-water. Okay. So, well, now we have when talking about air-to-air units, we can be referring to two different equipment, mainly. On one hand, we have the domestic systems, such as split or multi-split systems, and on the other hand, we have the rooftop system, which is much more focused in the tertiary sector. In the image here, we could see the well, in the lower bottom part, we can see a rooftop, and the first thing we can notice is that its resemblance to a usual air handling unit. Actually, rooftop systems are hybrids between air handling units and chillers. The white part in the image of the bottom right corner is the air handling unit, and the black part here is the chiller. Okay. In a general way, chillers' way of working is to extract the heat from a room and dissipate it to the outside. And air-to-air term refers to those chillers which not only distribute cold through air pipes, but also dissipate the subtracted heat by a heat sink with the help of a fan. Okay. So in this slide, this is an air-to-water chiller. These chillers are the most common systems in the tertiary sector. As the air-to-air ones, they keep their ability to dispose on water heat through the air, but in this case, the distribution is done with a liquid like water. Finally, we have the water-to-water systems in which the heat dissipation is done in a cooling tower. Cooling towers are used to reject unwanted heat from the chiller, and they use the evaporation of water to remove processed heat and cool the working fluid. Water-cooled chillers are normally more energy efficient than air-cooled chillers due to this cooling process. Okay, and here we have the main difference between, sorry about this, because, okay. The main difference between type of chillers are the performance as well as the existence of secondary units. As you can see, air-to-air units don't need a secondary circuit, and air-to-water needs a water pipes in the cold output to channel the cold water produced to an air handling unit. Finally, water-to-water needs also the cooling towers and also the pipes for distribution, for the correct distribution of the thermal energy. The best performance is achieved by the water-to-water systems. And the problem of the water-to-water systems is the Legionella. cooling towers are easily affected by Legionella if they don't have a good maintenance, a good preventive and corrective maintenance. So where they are used? Well, most of them, especially air-to-water and water-to-water systems, are used in mostly every situation, every location. But air-to-air units are mostly used in at homes, houses, or small facilities. Okay, so absorption systems. Well, absorption systems are basically a normal chiller. Let's put this here. Are basically a normal chiller, but instead of having a compressor, it has a generator which takes advantage of some systems of operation features, such as the lithium bromide. Compared to electrically powered chillers, an absorption chiller has very, very low electrical power requirements, but from an energy efficiency point of view, these chillers have very low performance, from 50 to 100. I remind you that normal chillers normally have, even they are quite old, normally have about 200% of energy efficiency. So this is quite a lot less, from 50 to 100%. However, this system can be fed with thermal energy, and this is an advantage because they are very, very interesting in isolated installations through solar thermal devices, or maybe in places where the heat can be obtained freely. Okay, now we're moving on into distribution systems. Distribution systems can be pipes, air ducts, or by air handling units. Okay, so pipe system is normally used for hot water, and it can be used for radiant floor, radiator system, or fan coils. And heat air ducts can be used for obviously hot air, and normally used for air-to-air units such as heat pumps or splits. Finally, air handling units, which are normally called AHUs, are normally for heating, for thermal energy distribution, and also air treatment systems. Okay, now what we have here is a profile view of what an air handling unit is. In this case, what we have is a 4-pipe air handling unit, 4-pipe AHU. And what you can see here is that at the left part of the screen, you're going to see this is the entrance of the air, the ambient air. This is going to be the exterior part, okay? And the air is coming through the air handling unit this way, coming through the filter, passing through the coils, both the heating and the cooling coil, and passing through the fan. The fan is here only to create a pressure difference in order to move the air in this direction, and then it just expels it into the room we want to climatize. In this case, this air handling unit is very special because it's a 4-pipe air handling unit. It has two coils. It has a heating coil and a cooling coil. And 4 pipes, obviously, because you have one for the entrance and another one for the return, so 2 here and two there. And you might be wondering why someone would like to have or would want to have this type of air handling unit. Why we should use both heating and cooling at the same time in an air handling unit? Well, that is because, for instance, in Spain, there are places where, especially in the south, where in winter, if you have a building that has 2 facades, one to the south and another one to the north, you could, in the one heading to north, you're going to need cooling, sorry, you're going to need heating, but in the one you have at the south, heading to south, you're going to use cooling probably, because the sun is hitting through the window and you just need cooling. So that's why this air handling unit exists. In the next slide, what we have here is another air handling unit, another profile view. I'm not going to explain it again, but just with one coil. This is the normal air handling unit, okay? Normal one. So, terminal equipment or terminal systems. Well, there are lots of terminal systems, but we're going to take a look of some of them. These are conventional radiators. I'm sure all of you are familiar with this. The heat exchanger principle is radiation and convection. They are really common in central heated systems, in residential sector especially. They have to work at high temperature. If you don't feed these radiators with more than 70 degrees, with water of more than 70 degrees, you're not going to acclimatize the room, sadly. So they need to get feed. They need to be fed with a high temperature water, more than 70 degrees. Also, another wonderful terminal unit is the underfloor heating or the radiation system, the underground radiation system. The heat exchanger principle is again convection and conduction, which is not in the radiation system before we talked before. This system is uniform. It expresses uniform heat all over the room, and the heat rises up to 2 to 3 meters. It is very convenient because you don't have elements in the walls, hanging on the walls, and it is made of polystyrene. And the wonderful thing is that they work with an average temperature of 35 to 45 degrees depending on the season. So it is very convenient, and it is really useful in both residential locations, residential buildings and office buildings, or even industrial buildings with high floors. Also, we have here the fan coils. Well, fan coils are pretty similar than the air handling units. They are exactly the same, actually. As you can see here, they have the air recirculation here. They go through the filter, they go through the fan, they go through the coil with the water pipes here, and they go then to the, well, I've just explained the other way around, but anyway, the air comes here, goes to the coil, then to the fan, and then to the filter, and then goes to the inside of the room. They are just smaller than an AHU, and they work with low temperatures as well, 35 to 45 degrees more or less. They can be used with condensing boiler, for instance, or with heat pumps, with chillers. So they're a pretty good thing to have. The bad thing is that the heat is not very comfortable. Okay, and there is finally also air conditioning outlets without a fan nor a drive. There are just simply apertures in the tubes, and simply by pressure difference, you got the room acclimatized. And finally, we have the ventilation systems. Well, let's end this lecture talking about the ventilation systems here. As you can see here, we are again facing the profile view of an air handling unit, And this is because this equipment is not only used for distributing thermal energy throughout the building, but also to ensure the air quality to be good. This is normally done by opening some hatches that lets fresh air inside the building, which helps air renovation. The way of working is to have probes, normally CO2 probes, that send a signal to the air handling unit to start renewing the air when the CO2 parts per million are high. And as the AHU, as the air handling unit, can easily turn off the coils, air renewal can be done without acclimatizing again. So that is a good thing to do. And well, this is the end of the lecture here. Thank you everyone for attending this lecture, and I will be looking forward to your questions. Thank you very much.